Ernest Rutherford confirmed that radioactivity involves 3 different types of radiation: alpha, beta, and gamma. Alpha radiation consists of positively charged helium nuclei, that is, 2 protons and 2 neutrons. The radioisotope americium-241, used in smoke detectors, emits alpha particles. The parent nucleus contains 95 protons and 146 neutrons, making a total of 241 nucleons. When an americium atom decays by ejecting an alpha particle, the remaining nucleus has only 93 protons. This is a new element called neptunium-237. The decay equation looks like this. Neptunium-237 has 2 less protons, 2 less neutrons, and 4 less nucleons overall. Positively charged alpha particles are affected by magnetic and electric fields, but because they are relatively heavy, they are only weakly bent or deflected. They have low penetrating power and are absorbed in a few centimeters of air or by a sheet of paper. Beta radiation consists of high-energy, negatively charged electrons, which are produced in the nucleus when a neutron changes into a proton and an electron. The electron produced is the beta particle. For example, cobalt-60 is a beta emitter used in medical radiotherapy, equipment sterilization, and irradiating foodstuffs. Here is the decay equation. Cobalt-60, with 27 protons and 33 neutrons, a total of 60 nucleons, emits a beta particle, or electron, and the daughter nucleus is nickel-60, with 28 protons and 1 less neutron. The total number of nucleons remains unchanged. Like alpha particles, beta particles are affected by magnetic and electric fields, but are lighter and more easily deflected. They cause less ionization than alpha particles, being smaller and with a single charge, but they can penetrate further. It takes several centimeters of aluminium to stop beta particles, and they will travel for a few meters in air. Gamma radiation is a form of electromagnetic radiation, like radio waves, heat, and visible light. It is found at the highest frequency end of the electromagnetic spectrum, after X-rays. Gamma rays are produced in the nucleus as part of a rearrangement of energy levels after the emission of an alpha or beta particle. For example, when a uranium-238 nucleus releases an alpha particle and decays to thorium-234, a gamma ray is also produced. Having no charge, gamma rays are unaffected by electric and magnetic fields. They have low ionizing power compared to alpha and beta particles, but being photons or packets of electromagnetic energy are the most highly penetrating of the nuclear radiations. Gamma rays are mostly, but not completely, absorbed by a lead shield several centimeters thick.
Larger nuclei can return to more stable arrangements in several ways. They can convert neutrons into protons and give off beta radiation, or kick out whole groups of nucleons, 4 at a time, in alpha radiation. Or they can simply split into other smaller, more stable nuclei. When this happens, we call it fission. Fission is different from the other forms of decay because it can be harnessed and controlled via chain reaction. Now let's consider what this means from an energy perspective. According to the binding energy chart, uranium has 7.6 MeV of binding energy for each nucleon, for a total of 1,786 MeV, while barium-144 has 8.3, and krypton-89 has 8.8. And the extra neutrons have no binding energy. So every time a nucleus of uranium fissions, we get about 192 MeV of energy. But U-235, left to its own devices, might take billions of years to decay. So we will want to help it along. We do this by shooting a slow neutron into it. It absorbs the neutron and briefly becomes U-236. Then it splits into krypton-92 and barium-141 and 3 green neutrons. Those 3 neutrons go to split other U-235 atoms into other daughters of more neutrons, and the process grows and repeats again. We can put the whole thing in water, and the daughter fragments and neutrons will be slowed by the water and cause it to heat up. Finally, we can use the steam to make electricity. This is how a nuclear power plant works. Ever since Einstein demonstrated the equivalence of mass and energy, physicists often give the rest mass of tiny particles like protons, neutrons, and electrons in units of energy. 2 convenient energy units are the electron volt, or eV, and its cousin, million electron volts, or MeV. Using these units, here are some facts that will come in handy. The rest mass of the proton is 938.272 MeV. The rest mass of the neutron is 939.566 MeV. Let's take another look at the chart of binding energy of atomic nuclei. And now let's talk about fusion. If we can take a nuclei of deuterium, which has 1 proton and 1 neutron in its nucleus, and get it to fuse with a tritium nucleus, which has 1 proton and 2 neutrons, we would end up with helium, 1 extra neutron, and some energy. And we would have the basis for an energy-making machine. Let's run the numbers and see how it works. The binding energy for deuterium is about 2 MeV. And the binding energy for tritium is about 8 MeV. So the total for the input items is 10 MeV. The binding energy for helium is 28 MeV, and the free neutron has 0 binding energy. Subtracting the 10 MeV from the 28 MeV reveals that every time this fusion happens, we liberate 18 MeV of energy. And that's pretty good. But there's a problem. Getting the protons and the deuterium and the tritium close enough together so the nuclear force fuses them together is hard to do on Earth. This is the energy that powers the sun and the stars. But the sun's gravity holds the fuel in place, while the high temperature gives the nuclei enough speed to overcome the electric repulsion.
It is only in the last 100 or so years that humankind has understood that the nucleus of the chemical elements is not always fixed. It can change spontaneously from one element to another. The name for this process is radioactivity. You probably already know something about the nucleus. It's much tinier than the atom. It's made of particles called protons and neutrons. There are electrons orbiting around it. And though the atoms can share or swap electrons when they bond together, the nuclei themselves never change. Right? Well, no. Certain nuclei are not stable in that way. This means they may change suddenly, spontaneously. The radioactive nucleus flings out a small particle and transforms into another element, just like that. For example, a carbon nucleus can eject a fast-moving electron and turn into a nitrogen nucleus. There are 2 different particles that can be emitted from radioactive nuclei, though never together. The very fast electron is known as a beta particle. If you know a little bit about electrons, you may be thinking, what was the electron doing in the nucleus in the first place? The answer is that a neutron in the nucleus spontaneously changed into a proton, which stayed behind, and an electron flew out as a beta particle. This is not what chemistry has taught us to expect. The nucleus is supposed to be stable. Neutrons don't change into protons, except sometimes they do. The other particle that emits spontaneously from an unstable nucleus is alpha. An alpha particle is 8,000 times more massive than beta, and it's a bit slower. Alpha is made from 2 protons and 2 neutrons. If we trap a lot of alpha particles together, we get helium gas. Alpha is a helium nucleus. Like the beta particle, we would not have expected a heavier nucleus to throw out helium. But again, it happens, and the nucleus becomes a new element. So, is radioactivity useful or just dangerous? Wherever you are sitting, it is quite likely that there is a device nearby which contains a source of alpha particles, a smoke detector. The source is radioactive americium. You are totally safe from these alpha particles, which cannot travel more than a few centimeters in air. Beta particles penetrate much further through materials than alpha can. Radioactive atoms are used in medicine as tracers, to show where chemicals travel in the patient. Beta particles are emitted and have enough energy to emerge from the body and be detected. There is a third type of nuclear radiation, gamma, which is not a particle at all. It is an electromagnetic wave, like microwaves or light, but it is actually 1,000 times more energetic than visible light. Gamma rays may pass right through your body. Gamma is used to zap the bacteria in fruit to increase its shelf life, or in radiotherapy to kill cancer cells. Radioactive substances get hot, and this heat can be used to generate power. This heat has been put to use in space probes and, in the past, in pacemakers for hearts. The more abruptly nuclear radiation is slowed down, the more damage it does to the atoms it hits. This is called ionization. Alpha causes the most ionization as it crashes into other atoms, and gamma the least. For humans, the most serious effect of radiation is the damage that it can cause to our DNA. Although alpha cannot penetrate your skin, if you inhale or ingest a radioactive nucleus, the health consequences can be severe. Radioactivity is both useful and deadly, but it is all around us as a background to the natural world.